All right, so thank you for joining me today. This morning, thank you for introducing me, Tad. So yes, I've been working at Rolly the past year and a half, doing specifically music, audio, Linux embedded applications. And so what I noticed from working there is that there's still a lot of there's a lack of people actually using embedded Linux on musical applications. And I was like, why is that happening, right? So I'm trying to understand that process, and that's what I want to talk about. So our agenda today is I want to show why you should use Linux, why you should use embedded Linux on your next product, on your next music instrument or something like that. And today, I'll be talking about around 30 minutes about that kind of stuff. And I will do a demo. Unfortunately, I just noticed that I forgot one of the main important cables for the Raspberry Pi, which is like a serial port cable, so I can communicate with the Pi, but I'll try to overcome that, okay? So we have a nice demo. And the last 10 minutes will be Q&A. So hopefully you guys shout me with a lot of questions. And one thing is important to know that I'm not going to go into like deep details about implementation specifics on Linux, because I want to be more like introduction to, I want to be more like a higher level talk on this regard. So yes, Linux is great, and then I will discuss a little bit why it's so complicated, why people say, wow, this is too complicated, it doesn't work well, or whatever, that kind of stuff. So why is that concept? And then how to overcome that, so we can fix that and actually use, and you will see that how simple it is actually, in fact. And then the demo at the end, okay? So at the beginning, I will do a little bit of context. So I don't know if all you guys are familiar with Linux. So Linux is a operating system kernel, monolithic type, and it is usually distributed with a GNU operating system as well. So that's why it's commonly known as GNU Linux. And basically on embedded Linux, that's what we do as well. We do mostly use GNU Linux on that, but we normally say just Linux, right? It was released in September 1991. It's been 25 years, so it's quite mature. It's licensed under the GPL v2, so it's free as in beer and as in freedom, so it's free and open source software. That's great. It runs on many platforms, many architectures and platforms. So all these platforms, we're going to focus on ARM though, because that's what's most commonly used on embedded systems. So each Linux release has around 13,000 patches from 1,600 developers, roughly, on the last few years. So it's a lot of people working on each release. And it's completely open development process model via emails, basically. So you send your patch in a mailing list, and people will review your patch, will discuss whatever needs to be discussed, all in open mailing list, so everyone can see development going on and what is going on. So let's discuss one of the benefits. I just said a few benefits right there. Just being GPL, in my opinion, is a benefit, and open model as well. There's no like main company controlling the kernel, the project. It's like a community based. For me, that's a benefit. Another other benefits I'm going to list here is POSIX and single Unix specification compliant, which means that any POSIX compliant system, it should be compatible, it should be portable to that, such as Macs and iOS as well, and Android, of course. It has a really stable user space API. So in fact, it's so stable that even if it's a bug, even if it's wrong, it will become a feature. It will not be changed, basically, because user space applications are relying on that API, and Linux has this strong opinion about not breaking user space. So it's really stable. So in fact, you can run applications that you built yourself like literally 15 years or more and still runs on a new kernel today. So that's pretty cool. On the audio side of things, benefits that I see is like true multitasking, proper memory management. We're going to talk about like true multitasking a little bit after the next slide. Proper memory management, so you have obviously access to virtual memory and lots of like caching happening in the kernel in block IOs and that kind of stuff. So you have that for free, basically, which is really nice, especially for loading samples, let's say. And multi-stack audio. We're going to also talk a little bit about that, what that means. Also, it's tested across many industries and devices. So this is the only really operating system and kernel that actually runs on your phone, on your watch, on your fridge, on a rocket, on a plane, obviously not controlling the plane, but like infotainment stuff on cars, and it's the same code actually running there. So a lot of testing going on, a lot of improvements going on there, which you can get as a basically free benefit. So it's easy to port to new platforms. So because Linux has this abstraction in the kernel of what we call platform drivers that are actually specific for a particular platform. So this abstraction allows, each subsystem has this type of abstractions, which allows easily, if you have a new board, let's say, that has a new USB host driver, new USB host controller, for example, you don't have to, change your MIDI USB gadget driver. You can just, a silicon vendor, let's say, will just implement this new driver for that particular controller, and that will be completely integrated in the rest of the system. So it's easy to port, and that's really, really important that's one of the biggest benefits on embedded Linux, I think. And another thing, because of that, is well supported by all the silicon vendors and board vendors as well, because they want you basically run Linux applications on their board and on their silicon. And my opinion here is like one of the most important things is that Linux allows the developer to have complete full control of the system resources. So, and that it means on every aspect of the software stack. So it allows you to control system using the kernel using system calls, for example, low-level system calls that are not allowed in a normal operating system, for instance, because you don't have root access, you don't have permission to do that kind of stuff, because there are other things running. And in a build that you can do on Linux, you can actually remove all these other things. You can customize your build to just run your application, your audio application. So nothing else is on, nothing else is also taking place and running at the same time. So you can do that kind of stuff. You can control the system in the sense that you can even change the kernel code if you really, really want to go deep into things. So that, for me, is like a huge benefit. And this allows, actually, you to generate code that is low latency and real time, okay? And I want to discuss that. So here's one example, just pure Linux, okay? We call vanilla Linux. Supports soft real time, right? And just by this is like just a normal like system call type of code. So you can do things like set the affinity. The affinity means that you are telling the kernel to schedule this thread or this process, this task, right? In kernel terms, only in a particular CPU. So you can get benefit of not asking the kernel to schedule to not take care of that particular. And also, you can get advantages of other things like L1 cache and so forth. So you can do this kind of things. Or you can, basically you could say, okay, my audio thread, I want to run always in this CPU, and I want to leave one CPU. I have like 4 cores. I want to leave one of these CPUs to just run low priority threads, let's say. So you can tell the kernel to do that. So you minimize the latency on the audio thread, right? And another thing, you can change the scheduler policy. So you could use, the most common in audio applications is the FIFO, because it's so simple, and it means that once that thing is running, the kernel will not preempt that until that task is completed, basically. Obviously, that's not a guaranteed, because Linux kernel is not a hard real-time operating system. An RQ might happen, and if there's no other cores free to do that kind of stuff, it will preempt, okay? But, like I said, you can overcome that by doing some clever coding. So, and there are other things, like that was introduced in recent kernel releases, scheduler deadline, which is basically like a deadline scheduler for real-time applications. So you can do even more complicated things, like you can tell the kernel, okay, this process, I want to put this process in a group, that this group is part of, it can only share this amount of resources, can only use this amount of CPU, can only run in that particular CPU, that kind of stuff. You can let the deadline scheduler to use its algorithm to handle that. So you can achieve, much lower latency than what you think about Linux, because usually people say about Linux, like high latency and all. Yes, if you don't use correctly, yes. Now I'm going to talk specifically about audio, and audio we can not talk about ALSA. ALSA is the actual sound subsystem in the Linux kernel that is used for many years now, and it stands for Advanced Linux Sound Architecture. It provides audio, timer, MIDI, and even power management functionalities if you care about that. So it splits the kernel and user space into components, in kernel and user space components. So that makes it easier to write applications. Obviously, this is a low-level thing, right? I mean, most developers will hopefully not use this directly, but still. It accurately describes the hardware capabilities. So also is designed in a way that you basically need to introspect the hardware, and the codec, for example, or whatever audio card is, so you know what that card is capable of, and then based on that, you do whatever you have to do. So this avoids doing extra emulations and extra work that is not necessary. So you can optimize your audio rendering algorithm. And also even describes topology of the hardware, because some, especially embedded systems on hardware, they can be pretty complicated internally, how things are connected and so forth. So it also describes that. So there's no, like I said, no emulation at the low level. So one example, you can ask also, okay, what does hardware support? And they also will say, okay, it supports like 2 channels, 16-bit for playback, and that other card supports 2 and 4 channels, 16 and 32 bits, but supports only 32 bits in 4 channels. I don't know, it describes, it actually creates like a map of configurations. It can be quite complicated if you wanna handle that, but it's really powerful. Also, it's fully modularized sound drivers with server and client architecture of plugins. This is for user space, which is really useful. This is one of the things I'd like to point out for the Bella guys, that maybe you guys can use this and write a plugin for ALSA, right? And then you can use ALSA API in your real-time system. Because today you don't, you just write directly into the buffer and stuff. So that would allow potentially ALSA applications to run in Bella. Okay, I don't know if that works, but I think it might be worthwhile watching. Also, and then plugins can be implemented with specific reasons, like for instance, why I'm saying that, because ALSA plugin, the default ALSA plugin is actually the hardware plugin. So that's why it goes through the codec stack. in the kernel. But if you write like a different plugin that doesn't, it shares memory and does other things, you can do that, and you don't need to go to the kernel. That's my point. And other things like you can do emulation, like resampling, and even I don't know if you guys ever heard of Pulse Audio, which is like an audio server in Linux. I'll talk about that. It implements a plugin in ALSA. So even if you open an ALSA card and start writing to the ALSA card, it will go through Pulse Audio directly, not to ALSA, not to the hardware directly, to the PCM directly. Also, MIDI is actually really powerful in Linux. It has two main APIs. One is called raw MIDI, which is only represent the hardware as lower level. It's pretty much like a serial port, basically. So you can open, read, and write to it, and has some other information there as well, but basically really simple. And the sequencer, which is really nice for applications, and that's what applications use, which is basically inside the core is an actual event scheduler that handles with many things like events, media events, also ports and clients events and timer events and so forth. So many things happening. You can do a lot with that. And also what allows you to create several virtual clients, which is basically application clients, and even network clients, and then you can route them together. So the kernel core will schedule and route all the media events to clients. So basically supporting MIDI, multi-client media, what people call. And other things like USB to serial, USB and serial to MIDI, USB gadget drivers, USB audio class 1.0, 2.0, and also gadget version. When I say gadget, it's like the device side of things, not just the host, it's the device as well. It provides ALSA lib, which is just a higher level library for applications, and ALSA utils, which is debugging and utility tools, which is really, really useful, and we use that a lot. And other things, but this is highlights. Linux also has audio servers like Pulse Audio, which is aimed for desktop functionalities, and Jack, which is aimed for low latency applications. And I get that a lot. Some people say, oh, so if you do embedded Linux, you're going to use Jack, right? No, actually no. You're not going to use any audio server, because why do you care about audio server? If you don't have multiple applications, streaming audio, why do you need? You don't need. So it's even lower latency than using an audio server, basically. That's the point of the talk. And also supported by many libraries that has good support, such as JUCE and Port Audio and so many others, okay? Now I'm just talk a little bit about JUCE and why it's good on embedded Linux. And JUCE has native code for ALSA and X11 if you want to do graphics. Also native POSIX support, which is shared between many platforms, so this is shared code, which is nice. Has also Neon SIMD for vectorized operations for ARM, right? This is really nice, in my opinion. Has really a small number of dependencies. For Linux, is just ALSA, curl for HTTP stuff, which is required by JUCE, and libx11 if you want to do graphics, really. And that and other things make it really easy for cross-compilation support via makefile, because this is important, basically, because cross-compilation is hard if you don't have good support for that. So JUCE has good support, so I'm going to show like it's really easy to do cross-compilation with JUCE, like with a project that was generated by like ProJuicer, right? And many other benefits, it's like a high-level audio framework that is really good and used for many applications. So basically, this is like a simple architecture we're going to see in an embedded Linux system, software architecture, right? So you have like the Linux kernel, like the hardware, Linux kernel, which does many things, and the user space Linux, right? One thing I want to point is you can see also core and the codec code is not the same thing. It's completely different. So if you really change your platform, this is like just one example, right? There are many more layers in that. But let's say if you want to do a different platform that has even a different codec in your board, you can just change that particular code, which is just the codec driver, and nothing else will change. Like the MIDI functionality in USB will not change. The USB audio class will not change, even if you change USB hosts as well, because of the USB core. And that's why I have here like a platform, which is this platform, represent the platform drivers, and other drivers and the scheduler. So they're like complete different pieces. It's modular, basically, the kernel. And then on the user space side, which will be, most of you will be concentrating on, is you have your application, which basically will use JUCE. So most of the time will be there. And if you want to take advantage of other stuff, like threading and some other libraries, you can. You know, it's up to you, basically, if you need that. So, but most of the time, what I will show here in my demonstration is that you don't need to do anything lower level, basically, if you use JUCE. So that's the idea. Okay, so it's great and all, but why so difficult, right? Why it doesn't work? So, okay, so and what I will show here is basically applies to any embedded system, okay? Why it's complicated? One reason why it's complicated is because of that. Look, embedded Linux runs usually on an SoC, with a system on a chip. And look how many modules this thing has. Like this is like 3 years old, and look at that. So this is IMX6 quad because it's like quad core. It's used on the Seaboard Grand, and it has like tons of things happening there. And for each particular module, each particular controller, you need like a code to control that thing, like a driver for that, right? So you have, for example, you have graphics. If you want to use graphics, you need drivers for that. If all the like DMA, clock, IOMux, timer, PWM on the side, even power management, you need drivers, specific drivers for this platform, okay? Not generic stuff. You have the abstractions, yes, but you need specific drivers to talk to this guy. Because this is, it's an ARM architecture, but this is, in this case, like Freescale's implementation. So on that connectivity side, you have like all the audio interface, like I2S, SSI, I2C for communicating with the codec if you want, even SPI. You get it, right? So this makes things complicated, right? Just by that. And then if you actually want to use one of these guys, it's like a basic, also like an audio architecture. But if you actually want to use that, you have to connect them together, right? You have to connect the audio line and I2S to a codec, to the speaker's microphone, let's say, the USB host with a MIDI controller, MMC controller to a micro SD card, and if you have sensors to GPIO, let's say, or even other things, it doesn't matter, right? So you actually, the implementation of that, you don't use everything. You use parts of the SoC, you use modules, you use components of that. So for that, you actually need to build a board, right? And the boards, because of that, they're completely unique, because they are implementation of the SoC for a particular reason. So that makes them completely different from each other. So imagine this, I have this Raspberry Pi 2 here, right? And this Raspberry Pi 2 here uses an SoC from Broadcom. If I use this SoC as well, and I build my own board, it will be different code running in my own board, because I'm using different things. I'm connecting things to different pins and so on. So that makes difficult in a lower level. makes complicated, right? And also, the nature of some peripherals are completely board specific. So some peripherals that use protocols like I2S, for example, has no enumeration step, for example. So you can't know in runtime the address of a particular peripheral. And GPIO, I mean, is completely generic, so you can use for anything. So you need to write code to understand for what you're using, right? So yeah. And I'm going to show one example here. The IMX6 again. So this company is called Boundary Devices. Just the IMX6, they make 5 different types of boards, and they run different kernel there in 5 different boards. Obviously, it's the same source code and all, but it's different code, actually, that is built to each board. You can see one uses a TWI BLE module, and the other one down uses like a Wi-Fi and Bluetooth module. So just the Bluetooth code in this case will be different, for example, right? And another example here is the same SoC, different board. These guys, they have 3 different boards for the same SoC as well. Different code again, even bootloader, because it uses different pins and everything. So actually we use the IMX6 racks on the Seaboard Grand. We use that module there. So the bottom line is that, you know, the software support, if you want to be generic and you want to be portable, that is difficult, especially in a scalable way, like in a way that you can, next year you can release a new software like quickly, okay, in a different board or a different platform. So that is very hard, and so that's not a particular issue that Linux faces. Actually, Linux solves a lot of these issues. I'm gonna show. So yeah, basically putting all these blocks together. You guys know, I mean, if you ever did like like firmware development, it's completely specific for that platform. You have to, if you want to change like a different DSP that you want to run your code, you have to sometimes even rewrite the code, because it will not, even the compiler maybe will not work perfectly. So yes, it's pretty difficult and annoying a lot of times, to be honest. Even for me that I'm used with this kind of stuff, and I was building for the Raspberry Pi 2 here like this custom thing, and it was annoying, to be honest. So yes, I understand. And now what we can do about that, right? So here are the embedded Linux community, let's say, solution for this problem. And you can see our heroes there, like the GNU hero and the Penguin hero, the Linux Tux. And we have to, this approach basically takes consideration that you need 3 specific things. One thing is a bootloader. Why you need that? Well, because like the main thing of the bootloader is to load the kernel to memory from usually an SD card. And it boots with appropriate parameters. So the kernel actually, when it boots, it knows where it's running, knows some configurations that it needs to know in prior when it boots. Linux kernel, obviously, because of the platform-specific drivers that I just mentioned. So you have to build the kernel with those drivers, otherwise that functionality will not work. And I think we call root file system, right? What is a root file system? So the root file system is actually literally a root file system. So, which is the file system that you have all the system information there, the system binaries, the system programs and configurations. And why is it like a higher level? Why is it board specific? Well, because yes, it's board specific, but it's platform specific in a way, because all the binaries that you have in a root file system is compiled for that particular architecture, right? So it can take advantage of that particular architecture. So if it's, let's say, an ARM A8 here, like Raspberry Pi, the compiler knows things about that CPU can handle hard float point operations, and it knows CMD, so it can use intrinsics when it does compile like compile your code basically. So it is, the binaries are architecture specific, okay? And the root file system is also board specific because it also has the kernel, maybe kernel modules that are completely specific for that board, so it allows the kernel to load those modules when you need. And also sometimes like firmware stuff and other things that, let's say if you have in your board like a particular, outside your CPU, you do have a different, like a DSP that runs something there. So you want maybe upload the firmware to that guy. So that firmware is completely board specific, right? So you have those files in the root file system. So we need a way to generate this thing, right? So that's the main thing that we want. We need a way, and this is hard, right? And that's what we basically call an embedded world. Basically, we call that an image. An image can be anything, really, but in our sense, is really all these pieces together that you put in an SD card, for example, and you turn on the board and it works, right? So this is the image. So you need a way to generate these guys in a way that works properly. And this is one example of an image, right? The Raspberry Pi example. Raspberry Pi X, in this example, like an SD card, right? Because you use an SD card to boot. And what happens that the bootloader from the Pi, which is like flash in the Pi itself, is a proprietary bootloader. It goes to that address and runs, bootloader configuration files there. And then in that particular partition, let's say you have the kernel, and then the kernel at that point, your root file boots where your root file system is. So this is one example of an image. So when you generate an image, you have to know like where to put things, right? But again, you don't need to do that because this problem is already solved. So that's why we do have build systems, and we have really good build systems such as this one called OpenEmbedded, or is also commonly known as Yocto, because Yocto is the name of the umbrella project that also takes care of this project. But this build system actually does a lot of this stuff and takes care of all these things that I said for you, and in the end, it generates an image for you. So that's pretty amazing. I mean, to be honest, when I started working on embedded systems years ago, before this OpenEmbedded and some other build systems, it was like really, really painful to do this. It was like really painful, like a bunch of bash scripts doing crazy things, basically. So with this build system, it's pretty cool because you only need to worry about these things that I highlighted. One thing is the metadata, which in this context we call recipes. Basically, is just, I'm gonna show what a recipe is, but a recipe is basically defines a configuration or build logic, packaging, and instructions on how to build the software and an image, for example. So you need a recipe, for example, for your application. If you want to release your application on an image and build an image with your application installed in the image, you need to write this thing, okay? But this, again, this is like for someone who's maintaining, like who's releasing the stuff. Not usually developers, they will not really do this, okay? And also you need to take care of the BSP, which is the board support package, which is like a set of recipes, like I just mentioned, which configures, which is specific for the board that you have. So what happens that most of these vendors, I said, they have BSPs for Yocto. So you can just download their BSP and they have all these configurations for their particular platform. And the Raspberry Pi has also a BSP that I used to build an image there, which is maintained by the community. So usually you don't touch that unless you do your own board, and then you kind of have to maybe, you can extend something else and then just reconfigure specifically for your board. It's not complicated at all. And then in the end, what we care is the image that is generated, which will be flashed to your product, right? To your device. And that's another thing I really like about this build system is that it also generates an SDK for this particular image. And this is really cool. So you basically have a specific SDK that has all the configurations used to build this image, has all the libraries and headers and everything used to build this image in a package that you can use to build your own application easily, right? So it's really simple to do cross-compilation. So I'm going to show you, like, simpler than using like most SDKs out there, really. So that's really, really cool. And just now I want to show like what we have for JUCE. So I implemented this JUCE OpenEmbedded support as well, because JUCE has its own particularities, right? Because it uses producer and so on. So basically, it is upstreamed the support for JUCE in a meta multimedia. Meta multimedia is just the name of the repository. So meta something is, they use meta whatever for repositories. So it's there. So on the build system support of things, if you want to write a recipe that has JUCE support, you just call this thing inherit JUCE, which is basically like an include type of thing. Like it's almost like in object-oriented programming, you extending like a class, basically. And the SDK support, you can generate an SDK with the ProJuice installed in the SDK. So you don't need to, you can, let's say you can ship this SDK without people needing to even compile their own producer, basically, okay? And this is like a simple recipe, it's like really simple, look at this. So you do like inherit JUCE, you tell like where my cool project is. The build system takes care of downloading and unpacking and zipping or everything. You just need to say, okay, where my juicer file is located in my build, in my source tree. This compile command, you have to run this OE run make, which is basically a wrapper function that has some other parameters around make, basically. Okay, so you need to in the build system context, you have to use this instead of make directly. So it's just make, basically. And then when you run make, you basically generate a binary, right? That's a normal JUCE application. So you have to tell the build system, okay, I want to, copy this binary to that directory and bin dir. And bin dir is like a build system specific things, but it basically, I want to install that on /user/bin in my binary, okay? That's really basically what's doing. But like I said, probably you guys will not even have to worry about this. As a developer, you will not do this this is like build system things, okay? Like usually maintainers and release people will take care of that. So, okay, so let me finish pretty quickly. Okay, so example of a build. What I did here, I used these repositories there, and then I set the machine and the distribution. Poke is like the default reference distribution, and then I just run this JUCE image, and then it generated the image I'm going to use here. So what I have here, I have an SD card that I generated this image. What time is it now? 11 o'clock. What time do you have to finish? 11:15. Okay. So, well, I will. Okay. Because really we don't have much time left, I will demonstrate to anyone who wants. Okay. I have actually a C-board here with me, because what I have here, I wrote. Let me show at least the application. Okay, so I wrote this little JUCE. Where is it? I wrote this little JUCE application. Okay, that this is it's just a JUCE application. And then if I come here, where I am. So I come here. I come to JUCE builds Linux makefile, right? I already have the makefile here. So if I just do make, for example, config release, I will build my my binary. This is like for Linux, my desktop, and this will build, and I can run this application. This application basically it gets this input from the capture driver, which is like a microphone, for example, and outputs to the sound card, so to the playback card. It just does that. But what I want to show is, okay, so I have my binary here, and if I do this, right, I have binaries like 64-bit, 4x86, 64 architecture, and so on. Now, what I want to show, imagine this. I have okay, I have my tool chain here. So now imagine this. I'm in the same folder, okay, and I'm using the SDK now in this different view. And you can see that I have the tool chain, all the tool chains here for ARM. And what I will do is, I will do the same thing. Release, make, parallelize that. And this will actually cross-compile for this particular image. So it uses all the specifics. So it's actually much more optimized in a compiler way than a normal x86 build. So let's wait a little bit. And if we check the type of the file, you can see it's like ELF 32 bits for ARM. So yeah, we basically just cross-compile. And then you, as a developer, that's what you're going to do. You're going to develop your application as like a normal desktop application, maybe, test on your desktop and so on. And then if you want to cross-compile to test on the device, you source the SDK, which loads the environment of the SDK, and then just run make again. And this will allow you to really quickly develop cross-compiled applications for your embedded Linux platform. So yeah, so we have like 10 minutes. Sorry, I can't really do the demos. But I mean, if any one of you wants to see what I have here, I have this application. I did some modifications in the application to do some cool stuff, which unfortunately I can't show. And I have also the Equator engine, the synth, which is the synth that we at Rolly we develop. And we develop for many platforms. So the same code, the same synth engine is running on embedded Linux on the Seaboard Grand. It's really the same guy that is actually running on a Mac, on your VST plugin or whatever. So, and what I did for the Pi, I basically just rebuilt using this toolchain. So instead of, now it supports the Pi, and I have it here. So, in a $50 computer, basically, you can have like a professional synthesizer, and you can plug the Rise and play pretty decently. So I have that here. If you guys want to see, please join me. And we have like 10 minutes, right?